Hi guys. So far, every distribution we've looked at is a discrete distribution. And let's think about how we were viewing probabilities to this point. So we take a block. It's kind of this picture I've given you guys, right? So this has size 1. And then we have a discrete space, so maybe if we think of flipping a coin, we have these scales. And the first one might be a scale that's heads heads, and then heads tails, and then tails heads, and tails tails. So these are outcomes of flips of 2 coins or something. And so what we want to do is we want to take this block and chop it up into 4 parts, and for each part we're going to stick it on one of the scales. So we end up getting these blocks of mass 1 over 4. So each of these blocks has size 1 over 4. And so we have these sample points. And in each sample point, we give a particular weight, which is our probability. But now then, let's talk about modeling something like how long will a light bulb work? And here, we can't just take some discrete set of points and give a weight to each point. A light bulb might work for, if we're going to go in days or something, it might be 60.322 days. Or say you're playing golf. So how far does your golf ball go? On a particular swing. And it might be something like 73.7689 feet or something. So in these cases, it's not going to be good enough to try to use some discrete set of points and put a weight on each point. So what we want to do is imagine that we take the entire real line. So now we've got the real line. And at each point there's a scale. So for every point in the real line there's a scale. So if we say this is 0, there's a scale at 0. There's a scale at 1, there's a scale at 2. But there's also a scale at square root 2, for example. And there's a scale over here at pi, for example. And every single point has a scale on it. And what we're going to do is we're going to take that block of size 1 and just set it on the line. So now then all these scales are detecting some weight, at least from 0 to 1, maybe. And so notice that this would go to height 1 as well. This kind of thing is what we're going to call a continuous random variable. So this is a continuous distribution. Whereas what we've been looking at so far is called discrete. So these are discrete distributions. So we're going to want to transition right now and start looking at these kinds of distributions where we want to have a scale at every single point in the real line, because whenever you hit a golf ball or you're looking at a certain amount of time or something like that, you could have any real number be the outcome. So let's take this kind of picture where we just take the block and set it on the line. So we have a line of scales here that are going to try to measure weight. And here's our block of size 1. And maybe we want to find the probability of the interval from 0 to 1 over 4 or something. So here's 1/4, and it's a little off, maybe here's 1/4, and here's 0. And we want to find how much weight is sitting on that. Well, what we do is we take the chunk of the block here that's sitting on top of it and figure out how much of the block is covering this part of the interval. So here it ends up being 1 over 4. On the other hand, maybe we want to find the probability of the interval from 1/2 to 1. And so for this, we would start at 1/2 and go to 1. And we would look at this chunk of the block here. And that chunk of the block has size 1/2, right? So 1/2 the block is covering the interval from 1/2 to 1. So that's what those scales, the amount of the weight that those scales would be picking up, because that's what's sitting on that interval. But maybe this description is a little bit funny. So we have like an infinite string of scales picking up this block. But if we get rid of the vertical lines in the block, notice that this is actually a function. So if we go on R and erasing the vertical lines, we just have something that's 0 until we get to 0, and then jumps up to 1, and then goes back down to 0. So it's the same picture except for I'm erasing the vertical lines. And this is a function which we'd call f of x. And the probability of a particular interval from a to b is going to be the integral from a to b of f of x dx. So remember that the integral gives you the area under the curve, and that's what we're really talking about over here. So what's the area under the curve? From 0 to 1/4, and that's of course 1/4. But it's the integral of 1 dx from 0 to 1/4 as well. So that gives us the area under the curve. Now, so far, we've got the block here. And the discrete random variables, we could take that block and chop it up and put a different part of the weight into each scale. Here, I would suggest more we think in the continuous distributions as we just want to squish the block. So if I take this block and I squish it and reform it, I can get other blocks. So, for example, or at least other shapes, I might have a triangle. So maybe I can squish it so it's like a triangle, but it still has area 1. And I could even push it over if I like. So maybe it looks something like this. And it's still got area 1. And I can even kind of pinch it off on the sides, so I could squish it so that it keeps going and going to infinity. And you might end up with something that does that, and it never hits 0, but it just gets closer and closer, and it still has area 1. There's just a really long tail. And we can make all sorts of shapes, and you can break it up if you like. We could have 2 different chunks of the block. Then maybe this is area. So we take this block and chop it in half, and take the top half and move it over. So maybe we have something here that's area 1/2, and then over here we have area 1/2. So each of these is area 1/2 and area 1/2. But the total area is still 1. And each one of these we can turn into a function called a probability distribution function. So if I just get rid of the vertical lines and look at the red only, so ignore that vertical line, now I have a function which has area 1. Here, likewise, this is a function with area 1, and so on. So these do go on forever in both directions. Here I would just take this. And what kind of properties are these functions going to have? So we're taking this block and it's sitting on a bunch of scales, so we can't go under the scales. And we can squish it around and move it. And we get this function, which we can call f of x. And so, what do we know about f? Let's call them the properties of f. Well, for one thing, f is sitting on the scale, so we know that f of x is always bigger than or equal to 0. Also, the area of the block is 1 that we started off with, and we can only squish it around on the real line. So the integral from minus infinity to infinity of f of x dx, so the area that's sitting on top of our real line has to be 1. And these are called, so f of x is called a probability distribution function. Or if we'd like to abbreviate, PDF. And I'll just note here that the PDF is related to the PMF. Remember, the probability mass function was the amount that we put on each scale. And here we still have a sequence of scales, but now then, well, not a sequence actually, it's a whole continuum of scales. And so it is different, but it's related, and we'll see some more relations in the future in the class. One thing that's certainly different, let's just take this particular function for an example. What is the mass at the point 1/2? If we just want to look at 1/2 itself and figure out what the mass is at this scale, well, it's just this line here, the amount of area in that line, which is the integral from 1/2 to 1/2 of 1 dx, because f of x is 1 at this point. But no matter what function that you put here, if you're going to integrate from 1/2 to 1/2, you get 0, right? And in particular, the integral from a to a of f of x dx is always 0. So each scale individually registers a mass of 0. But once you take enough of them together, a whole interval of them, then you get a positive mass. So you're going to have to take an interval. And that's a key difference between a PDF and a PMF, the probability mass functions. One thing we looked at also in the discrete case were the distributions. So the amount of mass up to a certain value x. And that's also going to be crucial for us to study in the continuous case. So what we're going to say is that if f of x is a PDF, the distribution f of x, or say f of a, is defined by f of a is equal to the probability of the interval from negative infinity to a, which, remember, the probability is measuring the mass on the scales, and the way we talked about doing that is we integrate from minus infinity to a f of x dx. And so this is the other important function we're going to want to talk about, are the distribution functions. Really quickly, let me cover the properties of distributions. And I may have to talk about it more in class, because I'm about out of time. But notice that the limit as a goes to minus infinity, negative infinity, of f of a equals 0. Because if a starts going down to minus infinity, we're going to go past all the area to the left. The limit as a goes to positive infinity of f of a equals 1. Because eventually, if we start counting the area of the entire real line, we're going to count all the area that there is, which is 1. And f of a is an increasing function. As we make a larger, so whenever a gets larger, f of a can only get larger, because we're just counting a larger area, and so the weight's only going to get bigger if we include larger areas. So that's all the time I've got for this video. We can talk about it, elaborate a little more in class if necessary. God bless you guys. I will see you soon.